So if you remember yesterday, we were looking at our formula for gravitational potential energy. Remember, we talked about where that formula comes from, but you don't need to explain that. You just need to know how to use the formula. We looked at some examples. Okay, so the lady lifting the dog here, we have a mass, we have a height, we're assuming on the Earth, so d equals 10. And do you remember, in all physics questions, you write the formula out, you put the numbers in, use your project. Okay, we looked at an example of the dog there, and I asked you to think about what would happen. So we calculated the gravitational energy the dog has when it's in the air, remembered to change the kilometers to meters. We calculated that, and I finished the lesson by saying to you, how much gravitational energy did it have just before it hits the ground? What has that turned into? Now, I hope you realise, obviously, that all the gravitational energy has disappeared now. It has changed into kinetic energy. So, in fact, that's the gravitational energy. It started when it's here, and it goes faster and faster and faster. The gravitational energy gets less and less and less. The kinetic energy gets bigger and bigger and bigger. Just before it hits the ground, all the gravitational energy is turned into kinetic energy. Of course, when it hits the ground, that kinetic energy will turn into heat and also into sound of the splat of the dog. Okay, and you did some questions. Okay, so we're going to move on today. So we now know how to calculate gravitational energy. We're going to look at how we can calculate kinetic energy. Now, I'm going to explain where the formula comes from. And don't worry about this. If you do A-level physics, you will have to explain this. You just need to use the formula. But I want to give you a rough idea where this formula comes from. So if you remember, if we push an object, we're doing work on it. And of course, the object's getting faster, if we're pushing a car or a bicycle. So our work this time is being converted into kinetic energy, and if we're pushing something that's getting faster, we'd have a velocity time graph. Okay, so how could we, how much work have we done? Well, we know work is force times distance. Now, we know from topic 1 that force is mass times acceleration. Remember, that's Newton's second law of motion. So the work would be the mass times the acceleration times the distance. Okay, well, the mass is the mass, obviously. Now, we've got a formula for acceleration, haven't we? V minus u over t. V is the final speed. U is the initial speed divided by the time taken. And, of course, we know that the distance is actually the area under this graph. Okay, so, putting that into a few more formulas. So we know the initial velocity here is 0. So that u is just going to disappear. It's just going to be v. We've still got t on the bottom there. Now, the area of this graph, this is a triangle, is going to be the base, which is the time, times the height, which is the velocity. So it's going to be v times t divided by 2. So we end up with this expression. Well, of course, v times v is v squared. Mass, m is mass there. We've got a t on the top and a t on the bottom, so they're going to cancel. We're going to end up with this 2 on the bottom. So we end up with a little formula here saying the work we've done is mv squared over 2. Mass times the velocity squared, only the velocity squared, divided by 2. And of course, what's happened to that work? It's turned into kinetic energy. So this is where our formula for kinetic energy comes from. Again, you don't need to explain that. Kinetic energy is mv squared over 2. Remember, it's only the velocity that's squared, not the mass. Another way of writing that, if you're going to divide something by 2, is to multiply it by a half. So quite often, this is written as a half mv squared, or mv squared over 2. So just be careful there. I think this first one is easier to deal with mathematically. I find as soon as people start multiplying by a half, that causes some problems. Okay, and as usual, mass is measured in kilograms, speed or velocity in meters per second. So let's have a look at a simple example of that. Okay, a bullet of mass 150 grams is travelling at 400 meters per second. So it's a high velocity rifle. How much kinetic energy does it have? So, as usual, okay, actually, I've made a mistake. Have you noticed what the mistake is? I've put gravitational potential energy. That should say kinetic energy, shouldn't it? So ignore that. Kinetic energy is a half mv squared. So that's a half times m. Now you notice I've changed this. Our formula works with kilograms. So to turn from grams to kilograms, I've had to divide that by 1,000. That's made it a little bit harder. Okay, times v squared. Remember, it's only the velocity that's squared. So if you put that carefully in the calculator, you get 12,000 joules. I must go back and change the slide before I forget. Okay, so if you think about it, when we throw things up in the air, I think you can just about see me here, I've got my small mole here. If I throw it up in the air, when it leaves my hand, it's got kinetic energy. As it goes up in the air, that kinetic energy turns to gravitational energy, and then when it comes down, it changes back again. The gravitational turns back into kinetic energy. So at the bottom here is when it's moving fastest. It leaves your hand when it hits your hand, so maximum kinetic energy, minimum potential energy because it's lowest. At the top here, okay, that's when it slows down. In fact, it stops at the top, so the kinetic energy is at a minimum, but it has the maximum potential energy. So we have this change all the time: kinetic, gravitational, kinetic. Okay, so at the start of the lesson, I asked you this question. We calculated yesterday that the dog in the aeroplane has 408,000 joules of gravitational energy. So just before it hits the ground, that gravitational energy has turned into kinetic energy. The dog's moving very fast. Okay, so that's how much kinetic energy it has when it hits the ground. Now we can use this. Okay, so I know that we calculated the gravitational potential energy of the dog when it was in the air. So I know that the kinetic energy, that changes in kinetic energy, that's the kinetic energy when it hits the ground. Now I have a formula for kinetic energy, so I can calculate how fast the dog is going. So let's do that. Okay, so I know that the kinetic energy when it hits the ground must be 408,000 joules, and I know that that's equal to mv squared over 2, or half mv squared. So let's do some mathematics and let's see if we can figure out how fast this dog is going. Okay, so I've just moved that. So 408,000, that's the amount of energy this time, is equal to mv squared over 2, or half mv squared. Okay, now let's do some maths here. So if I divide on 2 on this side, if I move the 2 on this side, it's going to be multiplied. Remember, that's the same as multiplying both sides by 2. Okay, and I know, so that's going to move over to that, that's equal to mv squared, or I know the mass of the dog is 12. Okay, well I can stick that in my calculator. 2 times 408,000 is 816,000, must be equal to 12 v squared. Okay, see what's going to do next? I'm going to divide both sides by 12, so that 12 will disappear. So if I divide both sides by 12, 816,000 divided by 12 is 68,000. 12 v squared divided by 12 is just v squared. And if v squared is equal to 68,000, of course v is going to be equal to the square root of 68,000. So it's 261 meters per second. Now this, of course, is assuming that there's no energy lost as air resistance. If this was in a vacuum, as the dog fell, when the dog hits the ground, it would be 261 meters per second. But of course, there's going to be friction, there's going to be air resistance pushing against the dog. And in fact, the dog will probably reach his terminal velocity. So in fact, in reality, when the dog hits the ground, he'll be going much slower than that. Okay. So there's a question sheet to do now. Okay. The question sheet will either be simply putting numbers into this formula, or one of the questions will be similar to this one here, where you're going to have to use the gravitational energy turning into kinetic energy. So use this sheet to help you when you're answering those questions. Okay, so it's getting a little bit harder now, a little bit more mathematical. Over the summer, you need to make sure that you're learning not only the formulas, but I think we all need to brush up a little bit on our maths, and particularly our algebra, when we're moving numbers around like this, because this is not going to go away, and as you get into slightly harder physics, mathematics becomes more and more important. I have a son studying physics at university, and the maths is very, very difficult. Physics becomes almost all very difficult mathematics.